We are live right now. Yes, we are live right now.
Okay.
Yeah. So, hello everybody. I heartily welcome Dr. Thomas Hurd. We are really happy to have you here as this is our symposium which is going on. Not wasting any more time further, I would like to ask you to start, and I will just, in case there are any questions from the student side, I will let you know after the session, after your session has been presented. Thank you.
Okay. Excellent. Yeah. No, it's really, really great to be asked to talk. This is probably going to be slightly random talk. I'll discuss bits of my research, bits of science communication I do, and some things in between. But I'm very pleased to be asked. And the idea of Qvolution to sort of explore quantum science in creative and accessible and inclusive ways is fantastic. And it's what makes us all better scientists and makes the quantum community even better. I will say as well, if when you get questions, if you put them in the chat, I will try and respond to them in vaguely real time as well, and keep an eye on that. So firstly, what is it I do? I'm assistant professor in quantum technologies at the University of Birmingham. And for me, this is the best job in the world. I get to lead a research group into quantum technologies, and I'll talk a little bit about what I research. I get to teach. I get to teach undergraduates about quantum technologies, and I get to be in a place that values outreach and science communication and public engagement at the university. And I'm able to go to events and support it in giving talks like this and making quantum more accessible and more inclusive. So we'll start with sort of a quite cliched in what is quantum. And like 10 years ago, we would ask Google. Now we ask ChatGPT. And okay, it spits out some answer talking about sort of the smallest possible unit of something. This might be energy, this might be matter, this might be a single photon, and helpfully tells us it's governed by quantum mechanics. So some kind of rules that look after how we deal with things when we get typically sort of very small. Now, this has kind of led in the past 10 years or so to the development of quantum technologies, which I've been involved in since finishing my undergraduate, about 10 years ago. And broadly speaking, there might be some sirens in the background. Broadly speaking, this has sort of three main strands, all of which I've got to be involved in and lead research in. So sort of sensing and metrology. So this might be making new dark matter or gravitational wave detectors, or sensors for magnetometry inside the brain. Quantum computing is obviously very big, very popular, and there have been multiple talks during Qvolution on quantum computing and quantum communication. So this idea of sending quantum information and maybe linking up different quantum computers. And I think this is sort of well depicted in the scene from Ant-Man, where it asks, do you guys put the word quantum in front of everything? And broadly speaking, the answer feels like yes. And this is because we have access and we've developed these new technologies and these new techniques. And there are so many applications that all of these technologies could be used for, some of which we just haven't dreamt up yet. And so a large part of creating more ideas in quantum is increasing the exposure that people have to quantum technologies, such that they can put the word quantum in front of everything and develop new technologies and new techniques. Now, I know there's been a lot on things like superposition and entanglement throughout all of the workshops given here. And I'll just say a couple of brief words on sort of quantum superposition and sort of scaling. And so don't worry too much about the sort of funny brackets around these objects, but we're just saying we have some kind of coin and we're putting it in a superposition. So this is harking back to Schrödinger's alive and dead cat. And one of the things that makes quantum so powerful, or quantum technology so powerful, is the sort of space you have access to, the number of possibilities that you're able to utilize, and the sort of space you're allowed to work in. And simply if you have, we'll call this a qubit, but this could just be an atom or any of the other things you've seen during evolution. And you have, say, 167 atoms. I didn't pick that number completely for random. Say you have 167 atoms, just 2 levels, 167 qubits. You've got an enormous range of possibilities of states that you can exist in, nearly 2 times 10 to the 50. And the reason why I chose 167, it's a comparatively low number. We can all visualize more or less 167 things. But it's roughly that number of possibilities, the number of possible states that you have access to is approximately the same as the number of atoms on the Earth. So if you were to label every one of those states you have access to from just 167 of your qubit or your atoms, you need to label them with an individual atom, and you'd run out by the time you used all of the atoms on and in the Earth. And that's pretty mind-boggling. And kind of, a lot of this talk is about how do we visualize some of the quantum technologies that we want to use, and how do we start to get our heads around it? And that's one of the sort of key ideas of science communication, is that sort of, being able to address different backgrounds, different experiences, where people are in their education. How do we convey our science to them? Okay, so that kind of, we've hinted towards sort of why quantum technologies. And then this is quite an old slide, but still sort of incredibly relevant, in that quantum technology has this interface of sitting on sort of physics, engineering and material science, and a long history of sort of information and computer science, where algorithms that you can do, or you can form on quantum computers, things like factor in large numbers, the theory has far surpassed what we can currently experimentally operate. And so, I'm an experimentalist. I work in sort of atomic and laser physics, and what we can do in the lab, we're pushing the boundaries there, but there's a lot of information from maths and computer science, and we're borrowing these materials and these novel engineering techniques, all to develop quantum technologies. And for me, it creates a really vibrant community of people with backgrounds in sort of all 3 of these sections, coming together, working together, and collaborating towards making the sort of next generation of technologies. So I'll go through a couple of little demos now towards how we might think of some of the sort of how we might use quantum technologies, and sort of ideas behind some algorithms. So we start with a sort of a simple problem that we might want to give our computer, and that you might use on a daily basis, although probably not at this scale. And we just ask our computer or some algorithm to put these numbers in order. And so it's comparatively straightforward, and we can just sort them by whichever method you want for, for 6 numbers or 8 numbers. We don't need anything too complicated. But if this list got very large, we start to think, okay, well, how many steps might that require? And we think, well, okay, firstly, I need to read all the numbers. I need to read them, decide how big they are, so assign some value, and then a method would, okay, I've read all the numbers, and now I'll put the smallest one at the front. Decide which of those numbers I've read is the smallest and put that at the front. I then need to sort of reread the remaining numbers and decide which one of them is again the smallest and put that next. And up to some sort of vague errors and vague scalings, we can. Now, this is not by any means the most efficient way to do this, but just to give you a flavor of the, when this guy scales, how computationally hard does this get? And broadly speaking, scales like n squared. So, we're going to need lots and lots of steps. If we multiply the number, if we double the size of the list we're trying to sort, the number of steps increase by. And that scales quite badly for our computer if these lists get very long. And I want to play a short animation by a researcher called Stefan Seeger. And this is called the spaghetti computer. And what we do is we take our spaghetti, we cut them to the right length of our list we want to order, and we just line them up. And, okay, this isn't, and then we put them in order, just picking the longest strand. We don't need to reread any of them. We don't need to sort of measure them. We can just line them up. And here we've kind of exploited another dimension. We've encoded that information in the length of the strands of spaghetti. And that's made it kind of trivial to then sort in terms of the number of steps. Obviously, actually doing this and cutting spaghetti of the right length takes much longer than your computer could do it. But then if we think of the sort of number of steps in this sort of toy model, we can think, okay, well, we took n steps to cut. We had to cut each spaghetti to the correct length. But then we just, lay them flat, lay them against the desk, and that was all sort of done in one. And then we just take each strand of spaghetti, the longest, we can trivially see which one is the longest. And this, this scales so much better. We no longer have that sort of quadratic scaling. And this isn't how quantum computers actually work per se. But this is an idea of how we can exploit, in this case, the length of the spaghetti or the length of something physical. How we can exploit these different facets that we have access to now if we sort of use quantum objects, how we can exploit that and improve the scaling for these kind of computations. And that's more or less what people who study quantum algorithms do. They try to think about, okay, how can I utilize this huge space I've got to play with, these huge sort of extra dimensions, if you like, which isn't that far off in sort of linear algebra land. How can we exploit these extra dimensions that I have access to in order to make our algorithms better than we know how to do on a sort of regular classical computer? And so the next sort of demo or sort of explaining tool I'm going to talk about is indeed the sort of title of this workshop, and is entitled Quantum Snakes and Ladders. And this was sort of born during lockdown. I was involved with a number of local high schools during lockdown and before and after lockdown as well. where I'd look to promote physics, promote access to university, these kind of things. And I was looking to develop ideas and tools to expand physics to now these students who are essentially stuck at home during lockdown, trying to learn at home. This was predominantly geared towards sort of 16 plus people, GCSEs to A levels in the UK. And how do we think about physics? And there was something I kind of noticed when talking to high school physics students was a bit of a disconnect, a little bit of a disconnect between math and physics when you're sort of 16 to 18, in that the mathematical tools you learn during that sort of GCSE to A level allow you to solve some physics problems, but not many. And even sort of what you might think of easy physics problems become very hard to solve analytically and with the math tools you have. And so an example of this is even just something like throwing a ball up in the air or dropping a cannonball off a tower. As soon as you include air resistance, which you can't really get away from enough, as soon as you include air resistance, no longer can you solve it analytically in high school, which is why all our high school physics problems are without air resistance, because actually dealing with the math of air resistance, even of a cannonball that the coefficient of friction and things with, is really hard. But what I also noticed, if you like, was that it's sort of 2 or 3 lines of Python to just put in the method called Euler's method, but put in the force. We know what the force acting on a cannonball of some velocity is, and it's 2 or 3 lines of Python to solve that problem with air resistance. So we have this tool now where students are spending a lot of time essentially stuck at home, and many of them were teaching themselves to code. And we're now able, and I wanted to give them the tools to solve some of these physics problems that were sort of inaccessible because the math was too hard. But actually sort of simulating or computing it could be done sort of very easily with sort of very basic understanding of Python. So it looked, and coding is an incredibly valuable skill to be able to develop. So I wrote these essentially Jupyter notebooks or Python workbooks for these students to develop their coding, to develop their physics intuition. So this idea, okay, well, like, what if I suddenly open a parachute? Can I get Python to plot the forces acting on it? Can I get it to plot the velocity, how my velocity changes? And develop, our intuition, be able to create, things with sliders and, dynamic physics problems that maybe you don't have access to in sort of pen and paper with some fairly rudimentary coding. This was not a sort of computer science lesson in what are types of variables and floats and things, but how do I simulate simple physics problems? And this kind of led me to write some Monte Carlo and Markov chains simulations, which I'll go into what they mean exactly. And to do that, I thought about snakes and ladders. And so this is credit to Nick Berry and John Burkhardt, who have both sort of created similar simulations to this. And okay, on the left, we've got Snakes and Ladders board game. I think most people are vaguely familiar with the idea of you roll a dice and you progress a counter. And we have some ladders where if you land on one of those squares, like 1 to 38, you go up them, and snakes, so like at 98 to 78, which you fall down on. And the idea of what's called Monte Carlo simulations, which is used at the highest level of physics to simulate things, is the idea of, okay, just repetition. How I just program my computer, and I say, okay, each turn generate a random number between 1 and 6, and add that to your current position. And then if I land on one of these squares, update my current position to this square. And if I land on one of these squares, update my current square to this. Okay. And there are obviously lots of clever ways in Python to do this, but ultimately, a lot of if statements saying, if my position equals 1, position now equals 38, will work just as well. And you can then run hundreds of thousands of games on your computer. And you can then look at, okay, how long did it take to complete the game? Okay. And you can see, the first game ended in sort of 6 or 7 moves, where, okay, you were probably very lucky and you got, to 28 very quickly. And that took you up, quite a lot of the board. Interestingly, you can also look at, and this is some of the exercises that my students did with this. You can look at, okay, what happens if I take a snake away? Is that always better? Does it always make the game better? And the answer was no. Not always, because sometimes, by taking, for example, this snake at 48 or 48 to 26, if you landed on that snake, you then have a second go of jumping on this enormous ladder. So there are all kinds of ideas that the students came up with and how to investigate, this board and what it looked like. And okay, most games finished in about 25, and that's probably fairly standard for for what children want to play in these board games and how long they want to roll the dice for. And this is just a sort of repetition method. So there's nothing sort of particularly complicated here. We just roll the dice again and again, finish again, and then see how long it took. And then we can think about, okay, 90% of games should finish in about 17 minutes. Okay. And that's, again, sort of probably what you want. In principle, games can go on forever. You keep getting stuck in some infinite cycle. But statistically, they will eventually end. And the students really enjoyed that. And then I thought about, okay, can we do this another way? This has worked really, really well. And being sort of vaguely quantum minded, I thought, okay, well, what about sort of probabilities? Quantum mechanics is sort of flush with these probabilistic ideas, these probabilistic operations. And we say, where will I be after one dice roll? And okay, well, we can kind of believe if we roll some dice, there's a 6 chance of ending up on one of these squares after one roll. Okay. And after 2 rolls, it gets a bit more complicated. We'll have explored sort of 36 paths and be on one of these squares. After 10 rolls, we've explored some huge number of paths, some of which have got to the end. And so there's some probability, we saw after 10 rolls, of getting to the end. But after 10 rolls, we can pretty much be anywhere on the board, except for sort of very low. These guys will be empty after 10 rolls. Okay. And we can see, okay, how does this change? And we can see, okay, as we roll the dice, that 100 square gets more and more likely to eventually got to. And this is sort of how we solve it. And this idea of sort of taking these paths, adding them all up in this sort of chain is called Markov chain. And I actually felt there were quite a lot of similarities here to quantum mechanics and quantum computing. This idea of, we're adding up many different paths that we've taken that are something probabilistic, and that you could imagine, okay, after each turn, roll in some kind of quantum dice, which maybe puts you in a superposition of all the squares and all the possible states you could be in, and then add in snakes and ladders after each turn to perform sort of gate operations on your quantum computer. And again, to that sort of scaling, that 10 rolls of the dice, where I said you could be pretty much anywhere on the board, about 60 million different possibilities. You roll the dice 10 times, and you're in some, you've explored 16 million paths on your board. And obviously, everything I've talked about here is kind of classical, but hopefully it starts to help how to conceptualize some of these quantum ideas, some of these difficult superposition, not an easy thing to get your head around. Okay, so I think, okay, well, maybe it just means I'm occupying these 6 squares on a snakes and ladder board. Maybe that helps, and people generally quite like this idea. So I'm about halfway through, and now I'm going to talk about equally exciting things. But there'll be some more board games, some more dice. And so this is going to be on my research. So as I mentioned, I'm sort of an atomic and laser physicist. I look to create ideally useful devices using sort of photons, atoms, lasers. And here are some of the experiments. So in this case, this is a cold atom experiment where within this project, we were looking at detecting gravitational tools that could in the future be used to detect gravitational waves and some dark matter candidates. And that little bright blob in the middle is some very cold strontium atoms inside the magneto-optical trap. So we have some atoms and we're firing lasers and we're putting magnetic fields around them and we're cooling them down such that they behave sort of quantumly, that we can then exploit them later. And within sort of my research group, and the research I do is this idea of quantum memories. And that's what I'll sort of focus on. This steers towards sort of slightly more quantum information, quantum computing, and sort of quantum communication. So the idea of single photons and photon quantum information. How could we use photons, and why do we care? So photons, they're wonderful, but they've got lots of different properties that allow us to encode information. So the most basic one, if we like, that we might think of is, well, okay, photons, we know they can be lots of different colors. And we know that we can vary the frequency of a photon from radio waves to gamma waves. And we can use that to encode information. We can use the frequency or color of the photon to encode the information. But there's other things. Many of you are probably very familiar with polarization, which is, we have a photon or a wave, and which way is it oscillating? Is it oscillating vertically or horizontally compared to its sort of direction of travel? And one thing that photons have over many other types of quantum information systems is they're actually, low noise, and these are sort of visible photons. They don't decohere at room temperature. There is no need, you don't need to cool them, you don't need to put them in a cryostat. Photons are incredibly robust, traveling at room temperature, which cannot be said for most other systems. And currently, as anyone who's got fiber broadband or fiber internet knows, we currently have huge optical communication networks in place. And if we can work out a way to use single photon and send quantum information, we have a lot of infrastructure and a lot of technology as well to do with sort of optical communication. And so broadly speaking, it's, whilst the platform for the ultimate quantum computer is sort of hotly debated, it's probably unequivocal that we're going to want to send quantum information, we're going to want to link things with photons. And this might be, we might use these photons to interface different nodes within a quantum computer. Or to send quantum information or entangle two things that are very far away for encryption purposes. And one of the tools in order to realize a lot of these sort of photon quantum information goals is called a quantum memory. Okay, and so this isn't sort of like hard drive memory or RAM. This isn't sort of quantum RAM or anything like this. It's, I say, a bit simpler than that. Broadly speaking, it's just some device that we can put our photon or our quantum state in, and we can keep it there and we can keep it safe. Because for all of those benefits I said about photons, one of the slightly frustrating things about them is that they move at the speed of light. And that means getting them where you want them to be, when you want them to be, can be quite challenging. Because you have to time everything very precisely and hope everything else is lined up. And places where you might meet these quantum memories. Here we have something that looks a bit like a photonic quantum computer. And we'll see a bit more of this in a minute. But we have various photons going in, and they're talking to each other, and these blobs sort of, are gates between these sort of two qubits, if you like. And we've got detectors here. And ideally, you want all of these photons to get to the end or get to these nodes simultaneously. And so we have sort of local networking. And as I said, these nodes might be from ion trap quantum computers or superconducting quantum computers in a cryostat, and you want to link them together. And then if you want to create sort of more global networking, you want to create entanglement between different places. Maybe you want to perform some cryptography between these places or key distribution. You're going to need to entangle. You need to quantumly link two things, and you're going to want to do that with photons. And quantum memory is this idea of being able to synchronize and send information a long way, and it requires these quantum memories. And so how do we think of our quantum memories with what's a nice analogy that we can use to understand this kind of probabilistic aspect and why we need them? And so we obviously go back to more dice games. Okay? And in this case, it's not snakes and ladders, but it's a game called Yahtzee, which some of you may not be familiar. And the aim of the game, broadly speaking, is you have 5 dice and you look to roll them and create certain combinations. So these combinations might be a straight, 4 or 5 dice, mapping out 1, 2, 3, 4, 5. Or they might be 3 or 4 of a kind. And so the way you do it, you roll your 5 dice, you see what you get, And then you have this ability to say, okay, I want to keep some of these dice. I might have rolled the dice, I might have rolled 5 dice, and I got 3 sixes. And that's pretty good. And I can keep those 3 sixes and then just roll the other 2. Okay. And now what does this, and that's how the game is played. And you look to sort of tick off these combinations. So what does this have to do with quantum memories? Okay, well, say you want 5 sixes. You want to roll 5 dice and get 5 sixes. The probability of doing that is about 1 in 8,000. Okay, of just being able to do that. So if you want to do that, you're going to be rolling those 5 dice for a very, very long time to eventually get 5 sixes. Okay, but what if, like in Yahtzee, I say you can keep it every time you roll a 6? Okay. Now, in that case, you just need a 6 to come up on every dice. And so after 6 throws, you could expect, if you want, that each one of the dice will have given you a 6 at some point. Okay. And so we turned 8,000 throws to 6 just from our ability to keep our dice. Okay. And as I said before, quantum mechanics, probability is inbuilt in quantum mechanics. When we explore that huge state, we're assigning a kind of probability to each of those states. And what happens, so here we've got sort of a photonic quantum circuit where we're putting in photons at this end and they're meeting at various points. So this was done on, sort of fabricating chips that you could put photons down and they interfere. But the kind of problem, is, okay, at each of these circled sort of nodes or junctions, what happens there is probabilistic. And it might be successful or it might not. And even if each one of these was 90% successful, if you want to scale this up to build our enormous quantum computers that can factorize large numbers, each of these are probabilistic, even at 90%. If we have 100 of them, we've still got 0.9 to the power of 100, which can be vanishingly small. And if you ask people who make quantum algorithms, okay, what do you want to do with 100 qubits? They say, well, could I have 1,000 qubits, please? Or 10,000 qubits? And at that point, these 90% success rates, or even 99% success rates, become vanishingly small. So in order to scale it, what can you do? Well, we bring back our quantum memory and we say, okay, store our successful attempts. When have we succeeded on each of these 90% probabilistic things? And now synchronize them. So we now retrieve them when they are needed, such that we don't need to roll 5 sixes or 100 sixes all at the same time. We just need to roll a 6 and keep it safe. And this is the idea behind some of these quantum memories and how you use some of these quantum memories, mainly towards sort of local quantum computing. But this ability to synchronize and cause these probabilistic events, store a successful outcome, and retrieve it when you need it. It gives huge power, and quantum memory has become a huge enabling technology towards it. I won't go into the nitty-gritty of exactly how to store sort of a single photon, but it involves atoms and lasers, and I'm always happy to talk about it. But to close, I just wanted to spend a couple of minutes talking about science communication and talking about public engagement, which I think is hugely important in quantum now more than ever. And broadly speaking, why to do it? And what do I think is important? Ultimately, to make science better. The more diverse science is, the better science is done. And the more accessible science is, the better science is done. And who do you want to communicate science to? Well, I mean, broadly speaking, anyone that will listen. And the impact that this can have is huge. You can talk about sort of inspiring children in the next generation. But there might be to adults, to parents, to encourage their children to explore science. This might be to policymakers and politicians and things who have a huge impact in how countries develop their science, which science country they want to pursue, and for how. Cynically, I'll say online conferences like Evolution, attending them, talking about them, sharing them. But I've also talked about science at music festivals. I've done exchange schemes with government and policymakers, where the idea where it can have a real impact, sort of a large scale, and what the understanding of science, and this all helps build trust in science and scientists, and accountability, because a lot of the time within universities particularly, but many industries as well, the government is putting money into supporting industries, and there's accountability and visibility to what public money is spent on, and I think everyone would agree the less misinformation there is, and we've seen hugely, COVID is about science in general and vaccines and whatever. The less misinformation there is, the better. And so, the more science and good science we can communicate, the better science and the better, hopefully, the world will be. And so that basically concludes this sort of fairly haphazard talk. I'd be really delighted, happy to talk about any of the things I've spoken about already, if there's any questions.
Yes, first of all, thank you so much for this workshop. I can see a few questions. The first one is, what do you think is the most common misconception people have about quantum physics or quantum technologies?
I think probably that they can do anything, and that they, maybe, hopefully it's not a misconception and it might materialize, but it's going to be a long time before we get a quantum computer to sit on our desk, and a long time before we get a quantum computer that can, solve anything. At the moment, there's lots of very hard problems that quantum computers can solve or assist in solving. But they aren't. There are limits to what they can do, and you can't just sort of say, "Oh, I can solve that with a quantum computer." And maybe a misconception that quantum is always better, and at the moment that's probably not true. People have worked very hard for a very long time to make our current computers as good as possible, and it'll be a little while till we surpass them in every aspect with a quantum enabled device.
Okay, and another one, how do you balance complex research with creating content that's accessible to younger students or the public?
Yeah, that's a great question. And time management is definitely a thing, and a thing I am not always very good at. But ultimately, even the highest level of scientists need simple pictures now and again to understand things. And I genuinely view it as, I am a better scientist for being able to explain my work and at all these different stages of people, be them 5 years old or collaborators. And the better I get at explaining my science, particularly asking people to fund me or work with me, the better science I can do. So I really value, the time I put into creating, accessible content and describing my research. I view it as an integral part of my complex research as well. How I balance that time is tricky, but it definitely has its importance.
Great.
Great. And also another one,
Yeah, please
what
continue.
advice would you give to young physicists or students who want to get involved in science communication?
I guess start small and practice. Try explaining things to your mum, or to your siblings, or to your granny, all of whom have, various different experiences. And the more, you might find, at the start, okay, I'm really good at talking to, 5 to 7-year-olds, but then they start asking harder questions. And I have the technical knowledge and how to answer those questions, but not how to put it at a sort of teenage level. And that just comes with practice and exposure. So just start small, in terms of just start small and talk to scientists, listen to how other people explain accessible content. There are hundreds of fantastic YouTubers and podcasters and things creating wonderful content at any level. And I look at a lot of quantum science communicators. There are a huge number, many of whom speaking at Qvolution and have been involved in Qvolution, and seeing how they talk about science, and what do they do, how much jargon do they use, is really useful for me in terms of getting better.
Okay, great. So the way you explained connecting games along with quantum was really exciting. Like it really attracts people to it. So as a researcher yourself, what do you think is the need of the hour in quantum right now?
Oh, so what's the need of, like, what areas of quantum do we need to focus on?
Yeah, yeah.
That's it's a really hard question. I think I would like to see some sort of re-emphasis on quantum for quantum's sake, I guess. And by this I mean, some sort of quantum technologies or quantum physics and ideas that doesn't have a direct commercial value now. And okay, because it's shown that, and this is why we do science research, is we don't know all of the applications for it, but we kind of trust that there will be, and that's why we fund blue sky research or things like this. And I think actually the most important thing in quantum, I think, twofold. One, to continue sort of some blue sky research that can be built into other things. But as I was answering, I think the other equally important thing is to bring in as many different expertise as possible. So when I showed that triangle about, you know, computer scientists and engineers and material scientists, I think increasing the visibility of the value they add to quantum is as important. And, you know, better science is built out of diversity in different people and different understanding, and borrowing the skills that the computer scientists know, but they don't know they know until they've had someone ask them, you know, okay, in quantum, how we can use this tool. And, you know, have you thought about how your ideas could be applied to this quantum technology? And no, they probably haven't, because they're not aware always of what the needs of quantum technology are, because they've not had them explained in sort of a way that they can understand. And so, you know, increasing the diversity of, you know, the tools that go into quantum technology is also very important.
Thank you. You have inspired by all these games ideas a lot of people. So yeah, we have come to the end of our session. Thank you very much for addressing us today. Yeah, Andrea.
Yeah, thank you so much again for this workshop.
No, pleasure.
It was
Absolute
great to
pleasure.
have you here.
Thank you.